Glycosylation isn't downstream of the process. It's not something you fix at the end after you've optimized titer and viability. Last time, in part 1, we covered the biology of how raffinose works and the experimental journey that led to a 2.8-fold increase in high mannose glycans. Today, we are getting practical. I'm going to walk you through when raffinose works and when it doesn't, and the exact 3-experiment protocol you can run in 8 weeks to validate it for your process. Let's dive in. First, let's talk about scope. Because raffinose is not a universal solution, and I don't want you spending time and resources on something that won't work for your program. Use raffinose when you need to increase high mannose for biosimilar matching. Specifically, when your cell line's baseline high mannose is 1 to 3% and you need to get, let's say, a 5 to 8%. That's the window where raffinose shines. You have room to move and the effect size is large enough to hit your target. Use raffinose when you have analytical bandwidth to track mannose 5, 6, 7, and 8 individually. If you're only measuring the total high mannose, you are flying blind. You need to see the distribution because raffinose shifts the profile towards mannose 5. If your reference product is heavy in mannose 8 or mannose 9, raffinose won't get you there. Use raffinose when you're in process development before you've locked your process for regulatory filing. Media optimization is expected at this stage and regulators understand it. It's low risk. Now, when should you not use raffinose? Don't use it if you need to decrease high mannose. If your baseline is already at 10 or 12% and you need to bring it down, raffinose will make it worse. In that case, look at feed strategies or temperature shifts to drive glycan elaboration. I don't recommend using it if your baseline high mannose is already above 10% because at that point it will be quite challenging to adjust it well by just using raffinose. And probably your media tweaks won't fix an underlying problem you have. You're probably better off by re-engineering the cell line at that time or using, as I've just mentioned before, some other media supplements. Don't use raffinose if you just need mannose 8 or mannose 9 specifically. Raffinose will give you predominantly mannose 5. If your reference product has a different high mannose distribution, you need a different tool. Kefenenzine might be your answer despite the cost and complexity, and so are other media supplements. And don't use it if your titer is already marginal, let's say below a few grams per liter. In that case, prioritize the productivity first. Get your titer up, then worry about glycan matching. You can't afford to take a 20% or even more or even a greater titer hit when you're barely viable. The key thing to understand is this: raffinose is tunable. The sweet spot for most processes is 15 to 50 millimolar. At concentrations above 65 millimolar, even with constant osmolality, you start seeing growth inhibition and titer hits. So you now have a working range and you need to find your optimal point within that range. That's what the 3-experiment protocol is designed to do. Let me give you the roadmap. 3 experiments, 8 weeks in total. And you will have a clear go-no decision point at each stage. The first experiment is a dose-response screen in 90-60 bull plates. Test 4 concentrations, 0, 10, 30, and 50 millimolar raffinose. Do this in your current basal medium. If you can maintain constant osmolality by adjusting with sodium chloride, this is critical because if you don't control the osmolality, you are back to confounding variables. If you can't, for instance, if you don't know the formulation, you can still do the experiment, but just factor in that you might have also, and you probably surely have an osmolality effect on top of what you're seeing. and track 3 things: the viable cell density, the titer, and the glycan profile at harvest. You need all 3 data points to make an informed decision. Your go, no-go decision is this: if you see at least a 2-fold increase in high mannose at 30 millimolar with less than 20% titer loss, proceed to experiment number 2. If you don't hit that threshold, stop here. Either raffinose won't solve your problem, or you need to do some either media or feed adjustment before you proceed. Perhaps even in certain cases need to revisit your cell line or explore other glycan control strategies like a temperature shift. Experiment 2 is a spin tube confirmation. Take your top 2 concentrations from experiment 1 and run them in spin tubes. Spin tubes give you a better metabolic profiling than the 96 T-pill plates give you. You can sample at every 2 days and track the glycan evolution over the entire culture duration. This is where you see if the high mannose increase is transient or stable. You can also look into some additional media additives, for instance, at day 3 or 5, and you can just see how that will impact your culture. And you need to know if raffinose holds through the harvest. And another optional thing, but it's insightful, is to measure, if you can, intracellular UDP galactose or UDP glucnuk if you have the analytical capability, because this will tell you whether raffinose is affecting the nuclear sugar pools, which would explain part of the mechanism. But if you don't have this capability, don't let it block you. It's not required for the go, no-go decision. Here is the go, no-go decision. If the high mannose increase is consistent across the time course and titer, proceed to experiment number 3. If you see other effects or other glycan species move, or even the titer is much lower, you likely have a problem and you need to do some additional media/feed optimization and probably adjust your osmolality along the way. Let's move on to experiment number 3, the scale up into benchtop bioreactors. This is where you validate the robustness. Take your lead concentration and run it in controlled pH and dissolved oxygen conditions, the environment your manufacturing process will actually see. And here is a tip. Challenge your process with stress conditions. Run one batch at a lower pH, run another at a higher dissolved oxygen, and also try to spike in glucose at certain days and to see if the metabolic stress affects the glycan profile. You want to know your boundaries before you commit to transferring this into the manufacturing process. The go-no decision is the following. If all 3 batches hit your high mannose target and you don't see unexpected issues, such as aggregation, charge variant shifts, a titer collapse, or some other glycans shift, you have a robust process. Document it, lock it in, and move to your next process development milestone. Let me share 3 mistakes we made during this work and how you can avoid them. Mistake number 1, I waited too long to involve the analytical. We optimized media formulations in 96 T-pill plates for weeks before getting our first glycan data back. We were measuring titer and viability, but we were blind to the quality attribute we were trying to control. The fix, well, if you can get analytical buy-in on day 1, and if you have some high throughput methods, sample at least at the very end of your 96 T-pill plate experiments. Make the analytical part your priority, and either you try to work with your internal capacities, or if not, for whatever reason, you can always outsource that to a CRO. Mistake number 2, I didn't map the design space early. Remember earlier when I said we tested raffinose at fixed pH? We never explored pH by raffinose interactions. We never tested temperature shifts. And we simply didn't check whether the raffinose effect would hold across different pH and temperature conditions combined, or even different PCO2 strategies. The fix is the following. Once you have a lead concentration from experiment 1, do a mini design of experiments. Vary the concentration of raffinose, change the pH, change the temperature, and look at how these interactions affect your mannose 5 species. Understand the boundaries and know where the effect is strong and where it's weak. That knowledge will save you when you hit an unexpected process deviation at scale later once you've validated the process. And that's an important remark I want to add here. This exercise is not just good for process development, but by doing that, you're also building an extensive process understanding knowledge base, which will be valuable once you have deviations in a manufacturing setting. Mistake number 3, I didn't check the feed interference. We optimized raffinose and basil medium and assumed the effect would carry over when we added our standard bolus feed on day 7. We didn't test whether feed components might interfere with the raffinose mechanism. So keep that in mind, because you're not just doing a batch, or very likely a batch run, you are doing a fed batch, and the feed has an influence on your process. Given what we learned about osmolality, that it can completely mask or confound the raffinose effect, feed interference could be equally substantial. Feed compositions vary widely and often contain components like manganese, galactose, or other supplements that could promote or inhibit glycan processing. The fix: test raffinose in your actual feed schedule from the start, and test higher and lower feed additions. The feed composition matters. Don't optimize your media in isolation and assume it will carry over. Include the feed. These mistakes cost time, they cost materials, they cost credibility with your manufacturing partners, but you can avoid them by planning more carefully upfront. Here is what this research taught me, and it goes beyond raffinose. Glycosylation isn't downstream of the process. It's not something you fix at the end after you've optimized titer and viability. Glycosylation is designed into the media optimization, or shall I say process development, from day 1. Most scientists optimize for titer first. They pick a cell line, they tune the feeds, they hit 3 or 4 grams per liter, then analytical comes back with Glycan data and it's out of spec. Now they're scrambling. They try temperature shifts, feed adjustments, maybe a late stage media tweak. It's reactive. What do the teams do that win? They co-optimize titer and glycosylation from the first design of experiment study. They set up their 96 depot plate screens with glycan profiling built in. They track high mannose, galactosylation, sialation, and fucosylation alongside titer and viability. They see the trade-offs in real time, and they make informed decisions about where to land on the productivity quality curve. Raffinose is one lever. There are others, and we'll explore them in future solo episodes. There's manganese, galactose, the feed timing, temperature profiles, but the principle holds. Your media is your glycoengineering platform. In short, media optimization can be a powerful way. It's faster, cheaper, and less risky than cell line re-engineering to optimize the quality attributes of your recombinant protein. If you lock that mindset in early, you will avoid the late-stage scrambles. You'll hit your regulatory milestones on time, and you'll save your team month of rework. If you want more details, you can access the full peer-reviewed paper in the Journal of Biotechnology. You'll find the links in the show notes. If you found this episode valuable, I'd love to hear your feedback. The best way to share it is by leaving a review on the podcast platform you found us on. It helps other scientists like you discover these insights and lets me know what's resonating with you. So I thank you already for your feedback. Thank you for tuning in today, and I thank you for taking this journey with me into media-based glycosylation control for biologics manufacturing. All right, smart scientists, that's all for today on the Smart Biotech Scientist podcast. Thank you for tuning in and joining us on your journey to bioprocess mastery. If you enjoyed this episode, please leave a review on Apple Podcasts or your favorite podcast platform. By doing so, we can empower more scientists like you. For additional bioprocessing tips, visit us at smartbiotechscientist.com. Stay tuned for more inspiring biotech insights in our next episode. Until then, let's continue to smarten up biotech.